All right, this will be for lab, the extra credit lab, uh, specific heat and latent heat. This will be related to chapter 13, 14, as far as temperature. So what I'm going to do is you have the data table that I'm going to go through. And what we're going to do is try and calculate the latent heat vaporization for water and compare it to the theoretical value. So I'm going to go through this using this cold bath. This is actually ice water, so it seems to be a little dirty, but we're going to start with a beaker, and I'm going to go through all the measurements here. So I'll end up going through the column here and doing the data using the Logger Pro. Temperature, which will get this down to about 1 degree Celsius. Then we'll start the time, and we'll record it in minutes. And what we're going to do is, once we get this going, I will help you. So we're going to go through the table 1. All right. So we'll start with a beaker, 100 milliliter beaker. The mass of the beaker is 126 grams, right? So it's 126 grams is what we're going to have for the beaker, the data table 1. All right, now I'm going to add approximately 100 grams of water, just water. Okay. All right, so fortunately I have exactly 100 grams of water. We're going to record the temperature. So it's at 2 degrees, and I'm going to then start the clock. Okay. And we'll start with this, and you'll see what I'm going to be doing. All right, so we'll take the initial temperature to be cold water mass, M sub 1. All right, cold water temp, initial temp, cold water temperature, 2 degrees Celsius. So that's what we'll have is 2 degrees Celsius. Now we're going to track this for a while. And all right, so I set the scale to 0 at the bottom, 100 degrees at the top, 0 seconds, and those seconds on there. So we're going to be recording the time, and we're actually looking for is when this thing starts to boil. All right? So it'll be a while as we watch this thing start to boil and raise in temperature. Okay. So the next the mass of the beaker plus H2O is 226 grams. From there, you can then get the temperature, the mass, the cold water mass. We start with M sub 1. So that will be M sub 1. You can calculate just by taking the difference of the two there. And the temperature was 2 degrees Celsius. All right, now we're going to do this. We're not really worried about how it goes up, but we're going to time it until it starts to boil. So we're up to about almost 4 minutes. I'll remove this. So it's just going to take some time. All right, we took a little break there. We're getting close to boiling. Close. All right, when it starts to actually boil, I'm going to get something going for you here. Okay, I would say it's now boiling at 11 minutes. 11 minutes and 10 seconds. Temperature of 97 degrees we had. There we go. 98. All right. 99 degrees. So temperature. So you can record the boiling point. Temperature we had is 99 degrees. And the time was 11 minutes and 10 seconds. Okay, we will now boil this for 11 minutes and 10 seconds. Or 11 minutes is good enough. So we'll go until we get to 22 minutes. And one thing I should point out as we boil this, as it boils relatively high, right, the temperature is not right. It's because the heat now is going into vaporizing. It's not changing the temperature of the boiling water, but energy is going into vaporizing that water. So we're going to do is boil this for till we get to 22 minutes. So we're putting the same, what we're going to do is try and put the same amount of energy it took to boil it and go from there. Again, we're not worrying about this temperature because I have the probe is sitting outside now. And we're only worried about the time. We got about 7 minutes to go. All right, I got 6 minutes to go. Okay, we got about 2 minutes. All right, about 1.5 minutes. All right, 1 minute. $30. All right, few seconds here. Okay, we're now going to put it on the scale. And we see that weighs the beaker plus the hot water weighs 204 grams. So the beaker plus the hot water. Now remember, the original mass of the beaker is 126 grams. Take the temperature of it. And all right, so now I'm gonna get some ice. Lab, I'll be going over this on specific heat. And latent heat. All right, I took the data I just did the experiment. So now we'll go over the lab handout, which is on lab extra credit, along with the rest of the video. And I'll go through parts of the data table with you, as far as what things you need to calculate. I'll get you started on that. A couple things here. we taught, again, specific heat, which is given the letter C for water. Again, we're all doing H2O, is 1 calorie per gram degrees centigrade, right? Latent heat of fusion, which is heat, is 80 calories per gram, and that's to melt ice. And latent heat of vaporization is 540 calories per gram. And that's to evaporate water. All right, so a couple things here. So this is what we did. Again, these are on the handout, so I'll go through part of the data table with you as far as what we did and how we did everything. So normally you would be doing all this data yourself, but I'll go through it with you so you can answer the quiz questions and at least understand what's going on. All right, so I'll erase this for now. Go through the first part. And so, again, go over what we did. And so we had the beaker mass. We had, so our cold water M1 was 100 grams. All right, and we started at a temperature of 2 degrees Celsius, more or less. All right, we then heated it until it started to boil. So the boiling point was, we boiled it at 99 degrees, which is about right for Bemidji because the boiling point changes with altitude, and we're at about 1,300 feet or so, so this isn't too bad. And so the change in temperature, delta T, was 97 degrees Celsius. All right. You know, we went through the beaker mass. I've shown those calculations in the video. Now, what we did is then the Q, which is the heat, is given by M, the mass, times the specific heat of water, times the change in temperature. That's how much heat we added to the water, was this. So that was 100 times 1 times 97, which is 9,700 calories. All right. Now we did this, the time was 11 minutes and 10 seconds, as we saw. So approximately 11 minutes is good enough. So that's how we did it. Because then once it starts to boil, what we do want to do, we assume in 11 minutes this is how much heat we apply, because we started the temp boiling as soon as we put the cold water on the hot plate, boiled it for 11 minutes. So based on the amount of heat it raised, we're now going to boil it for another 11 minutes, assuming this is the amount of heat applied. So we then go back, right? So this is what we do for the first part of the table, is we complete this left side, right? So I'll leave that up for a minute. Okay. All right, then we want to do the right side of the table. Okay, so I'll leave this, I'll erase this. I'm going to rewrite that anyway because I want to keep that in mind. So again, the amount of heat we applied, Q MC delta T, was 9,700 calories. All right, now the amount of water we started with, water was 100 grams. Now, and doing the calculations, you'll realize we started with 226 grams total. This included the beaker. We ended up, so water was just this, the total was this, we ended up after boiling for 11 minutes, it was 204 grams left. All right? That means we've lost 22 grams, right? So 22 grams of water evaporated, vaporized. Right? So that was vaporized, converted to steam. So how much heat is that? All right. Now, this is for just heating. This is the expression, as we've seen. For boiling, latent heat, and again, the reason we have latent heat is that it's it's hidden heat. As we showed, as the water boils, the temperature doesn't get any higher. It just boils away. So we have latent heat of fusion, which is mass times Q times LF, and for boiling, mass times LV. All right, so that's the amount of heat. So that was, we did it for 11 minutes. We're looking at vaporization. This was 9,700 calories. All right. Then, since we ended up, the amount of water vaporized is 22, then latent heat of vaporization would be how much energy did it take to vaporize each gram. We divide this by 22, and we end up with approximately 440 calories per gram. Okay, so we're assuming, based on cooking it for 11 minutes, we applied this much heat. That's how much that evaporated. So the amount of energy per gram was 440 calories. All right, now we then even that up. As we said, theoretically, under better conditions, latent heat of vaporization is 540 calories per gram. So then they get the percent error. This is theory. This is our experiment. I'll let you do this. Percent error or percent difference is theory minus experiment over theory times 100. And you'll see we're relatively close to the actual theory based on the uncertainties, like exactly how much, when did it actually start boiling? Did we actually apply that much heat? But it's relatively accurate as far as that is concerned, as far as this worked out. So that's that part there, okay? So that should be able to answer all the questions for the quiz for this extra credit lab. All right, now, the second part down here at the bottom, I'll go through that with you because I wanted to do a little bit on melting ice and do the example here. So I'll leave this up. All right. So we'll move on to the next part. And I have, for the chapter related to heat and specific heat and such, I've done some other examples. But what we did is I then took this 78 grams of water that was left, 78 grams hot water at approximately 95 degrees Celsius. Cooled off a bit because once took it off, had to then put the ice in, put in 50 grams of ice. All right. So I had the hot water, threw in 50 grams of ice, and then it melts, and we end up with just water at some temperature. All right, so I measured the temperature, and it was 24 degrees Celsius. All right. So that's the final temperature. Hot water, we take hot water, which is at 95 degrees. We have 50 grams ice, which is at a temperature of 0 degrees Celsius. Mix them together. So hot water is going to lose heat. The ice is going to gain heat. So how do we do that? All right, heat gain equals heat loss. And I want to try and calculate what the actual final temperature should be. So the heat gain will be, we have to melt the ice, M, and we're using M ice times 80 because we got to melt it, plus mass of the ice times T final minus 0. All right? And then what we're going to have, so that's going to be gain. Loss will be the mass of the water, and that's M2. Okay. Times 95 minus T final. All right? So this is what it should theoretically be, and see how close are we to that. All right, so it's going to be mass of ice. So that's going to be mass of ice times 80 times mass of ice plus mass of ice times T final equals M2 times T hot, using the same, that's this 95, right? And minus T final, and then we end up with T final as we have in the handout. If I solve for T final, is T hot times M2 minus 80 times M ice divided by the sum of the two. And you can calculate that yourself. I'll let you plug that in. Because T hot is 95, mass 2 is 78, mass of the ice is 50. And so on. So you can calculate that and see how close you are. It should be relatively close to what we actually measured, 24 degrees. So that's using latent heat of fusion of ice. Again, for the latent, that's Q is M ice times L fusion. So that's where this 80 times M ice comes in. So that's the extra credit lab as far as that's concerned, and that's the final lab for this semester, all right? So